Hi everyone, this is Srikanth S, Assistant Professor of EEE Department. In this session, I'm going to cover the concept of small signal models and common emitter amplifier. This is the basic common emitter amplifier circuit. Here, these are the resistors included in order to limit the currents, and this coupling capacitor is also included in order to set the impedance corresponding to the emitter junction. And here transistors amplifiers is going to amplify the AC input signal that alternates between some positive value and corresponding negative values. Then some way of presetting a common emitter amplifier circuit configuration is required so that the transistor can operate between these two maximum or peak values. So whenever we have given the AC input, which is going to have one positive peak and one negative peak, so the transistor has to operate under these two peak values, and this can be achieved using a process known as biasing. So this biasing is nothing but base junction should be forward bias and collector junction should be a reverse bias. Then the transistor will be in active mode. So the transistor will act as a amplifier. Here the biasing is very important in amplifier design because the transistor should be in active mode. In order to make the transistor should be active mode, the biasing is the very important thing in the amplifier design, as it establish correct operating point of the transistor amplifier. Because once the biasing is perfectly done, that is going to provide us the operating point for the transistor amplifier, and which is ready to receive signals and thereby reducing any distortion to the output signal. Also, the use of a static or DC load line drawn onto the output characteristic curves and amplifiers allows us to see all the possible operating points. So whenever we have take a DC load line onto the output characteristics curves, which we are going to get the number of possible operating points where the transistor is from fully on to fully off, and to which the quiescent operating point or Q point of the amplifier can be found. So where with this we are going to get what is the Q point of the amplifier, which we can found in the output characteristics. Here the main aim of small signal amplifier is to amplify all the input signal with the minimum amount of distortion possible to the output signal. So our main aim with this small signal amplifier is, with a small input which we are giving, based on that we have to generate the output with less distortions. That is our main aim in the small signal amplifiers operation. In other words, the output signal must be an exact reproduction of input signal, but only bigger value. So the output will be exact reproduction of input, but it should be of bigger value, that is amplitude of the output voltage or current is going to be increased. To obtain low distortion when used as an amplifier, the operating quiescent points needs to be correctly selected. So when we have taken the operating point, based on the operating point, we are going to get the different distortions in the output. So we have to choose the operating point such that where we are going to get less distortions. And this is in fact the DC operating point of the amplifier, and its position may be established at any point along the load line by a suitable biasing arrangement. Here, the best possible for this Q point is as close to the center position of the load line. So the best possible position for the Q point is we need to choose a point such that at a center point of the load line as reasonably possible, thereby producing class A type amplifier operation, that is VCE is equals to half into VCC. Collector to emitter voltage is equals to 50% of collector to collector voltage. Consider common emitter amplifier circuit shown below. Here is the input, and here we are giving the capacitors C1 and C2, and here are the resistors R1, R2, RL and RE. Here this VCE value is equals to half into VCC value. Here is the VCC value we are having, and VCE value should be equals to half into VCC. We need to make the arrangement such that we have to choose the point Q point for this particular circuit by making VCE value should be equals to half into VCC. A single stage common emitter amplifier circuit shown above uses what is commonly called voltage divider biasing. How we can get the VCE value as half into VCC? That is by using the voltage divider circuit. So this type of biasing arrangement uses two resistors as a potential divider network. So here we are having the resistors. These resistors will be acting like a potential divider network across the supply with their center point supplying the required base bias voltage to the transistor. And voltage divider biasing is commonly used in the design of bipolar transistor amplifier circuits. And this method of biasing the transistor greatly reduces the effects of varying beta value, where beta by holding the base bias at constant and steady voltage level allowing for best stability. So when the beta value is nearly constant, we are going to get a steady output voltage. The quiescent base voltage is determined by potential divider network, which is formed by the two resistors. So quiescent base voltage we are going to get by using the voltage divider network, where R1, R2 and power supply VCC as shown with the current flowing through both the resistors. Then the total resistance will be equals to R1 plus R2, giving the current as I is equals to VCC by RT. That is according to Ohm's law. Current is equals to voltage by resistance. And when these two resistors are connected in series, the equivalent series resistance will be R1 plus R2. So I is equals to VCC by RT. And the voltage level generated at the junction of resistors R1 and R2 holds the base voltage. At the junction, whatever the voltage we are going to get, that voltage holds the base voltage, and that value is constant at a value below the supply voltage. Here, these are the R1, R2 resistors we are having VCC, and here is the total current IT which we are going to get, and here is the IR2 is the current, but both are in series, so the current will be same, but here it is connected to the base, so base current will be reduced from this divider circuit. So here IT is the total current, where IT value is equals to VCC by R1 plus R2. IT is the total current. And here IR2 value is, IR2 is nothing but IT is the entering current, IB is the leaving current. According to Kirchhoff's current law, IR2 is equals to IT minus IB. IT minus IB. So the voltage across R1 and R2 is equals to whatever the current flowing through that particular resistance, which is multiplied with the current. So VR1 is equals to IT into R1. VR1 is equals to IT into R1, and VR2 is equals to IT minus IB into R2. VR2 is equals to IT minus IB into R2. So like this we are going to get VR1 and VR2 values. Now the potential divider network used in the common emitter amplifier circuit divides the supply voltage in proportion to the resistance. So whenever we have taken the potential divider circuit, which consists of two series connected resistances, so this will produce the output voltage which is proportional to the resistance. And this bias reference voltage can be easily calculated using the voltage divider formula below. That is, transistor bias voltage is equals to VB is equals to VCC into R2 by R1 plus R2, because here R2 resistance is connected across the base junction. So that's why VCC into R2 by R1 plus R2. This is the transistor bias voltage, and this value is proportional to the resistance which we have connected across the base terminal. As the same supply voltage which also determines the maximum collector current when the transistor is fully on, that is nothing but when the transistor is under saturation. When the transistor is fully on, the collector to emitter voltage is 0, but which will gives us the maximum collector current, where the base current for the transistor is found from the collector current. The base current is going to be found from the collector current IC, and the DC current gain beta of the transistor. So the base current for the transistor which is found from the collector current, that is IC, and the DC current gain beta of the transistor. So in this we can get the base current value, because the current gain is going to give us, current gain is nothing but output current by input current. When we know the output current, collector current and beta value, then we can get the base current. So we can calculate the base current by using collector current and the beta value. Here the beta value is nothing but output current delta into IC, change in collector current by change in base current, or we can also write if it is a DC IC by IB. A transistor's beta value, sometimes referred to as HFE on data sheets, which defines the transistor's forward current gain in the common emitter configuration. Here, this value is referred as HFE on the data sheets, which defines the transistor's forward current gain in the common emitter configuration, where beta is the electrical parameter built into the transistor during manufacture. So this is the electrical parameter because output current by input current, it should be matched with the transistor's performance. So based on the input, the transistor has to turn on. So this value will be given by the manufacturer, and it is the manufacturer is going to take this value into consideration while building the transistors. And where beta has no units, as it is fixed ratio of two currents, where beta has no units because it is the ratio of two currents, output current by input current. So amperes will get cancelled, so there are no units for the beta. Where IC and IB are so small, so a small change in the base current will cause a large change in the collector current, because IC and IB are, so a small change in base current also will gives a large change in collector current, because input values are small and the output values are high. That is the amplifier circuit. So even though a small change in the input will result a large change in the output, that is, but if IB value is changed with a small value, the collector current will be changed with a very high value. One final point about beta: transistors of the same type and part number will have large variations in the beta value, which is regarding beta, the transistors of the same type and part number also will have a very great variations in their beta value. For example, BC107 NPN bipolar transistor has a DC current gain beta value between 150 and 110 and 450. This is the data sheet value. So one BC107 may have a beta value of 110, while another one may have a beta value of 450, but they are BC NPN transistors. So in the BC107 itself, different beta values we are going to get the range between 110 to 450. Any transistor may have the values within the range, but they are both are BC107 NPN transistor. This is because beta is an inherent characteristic of the transistor's construction and not of its operation. Here beta is an inherent characteristics of transistor construction and not of its operation. Beta is going to have a great importance while going for the construction or during the manufacturing process, but not in the operation wise. Here, as the base to emitter junction is forward bias, the emitter voltage will be one junction where voltage drop different to the base voltage. Here, in order to make the transistor a perfect bias condition, we are going to make the base to emitter junction is forward bias. The emitter voltage V will be one junction voltage drop different to the base voltage. If the voltage across the emitter resistor is known as the emitter current, that emitter current can be easily calculated using Ohm's law. This emitter resistance is available when the voltage across the emitter is known to us. We can easily calculate the emitter current because according to Ohm's law, the current flowing through any resistor is equals to voltage across the resistor divided by that particular resistance value. Now the collector current can be approximated since it is almost the same value as the emitter current. Because the base current is very small, we can consider the collector current and emitter current are nearly same. Now let us go with one example. Common emitter amplifier, example number 1. A common emitter amplifier circuit has a load resistance of 1.2 kilo ohms and a supply voltage of 12 volts. Calculate the maximum collector current flowing through the load resistor when the transistor is fully switched on. Assume VCE value is 0. Also find the value of emitter resistor and RE if it has a voltage drop of 1 volts across it. Calculate the values of all the other circuit resistors assuming a standard NPN silicon transistor where IC max is equals to VCC minus VRE by RL, that is equals to 12 minus 1 by 1200, which is equals to 9.2 milliamperes, and where here VCE value is given as 0 under saturation. This establishes point A on the collector current vertical axis of the characteristic curves and occurs when VCE value is equals to 0. When the transistor is switched fully off, there is no voltage drop across either resistor RE or RL as no current is flowing through them. And then the voltage drop across the transistor VCE is equals to the supply voltage VCC. Then this establishes point B on the horizontal axis of the characteristic curves. Here generally the quiescent point of the amplifier is with zero input signal applied to the base. So the collector sits about halfway along the load line. Here Q point, which is considered as VCE, is taken as VCC by 2. So the collector sits about halfway along the load line between 0 volts and the supply voltage, that is VCC by 2. Therefore, collector current at the Q point of the amplifier will be given as ICQ is equals to 12 minus 1 by 2 whole divided by 1200, which is equals to 5.5 by 1200, which is equals to 4.58 milliamperes. Now we got the collector current. Now this static DC line produces a straight line equation where whose slope is given as minus 1 by RL plus RE, and that it crosses the vertical IC axis at a point which is equals to VCC by RL plus RE. Here the actual position of Q point is determined by using the mean value of base current. Here, as the collector current is also equals to the DC gain of the transistor beta times the base current. Here we assume the beta value for a transistor of say about 100, because 100 is a reasonable average value for low power signal transistor. So for low power signal transistor, we are going to consider the beta value as 100. So the base current IB flowing into the transistor will be given as, where beta is equals to IC by IB, where IB is equals to IC by beta, which is equals to 4.58 milliamperes by 100, that is equals to 45.8 micro amperes. Now, instead of a separate base bias supply, it is usual to provide the base bias voltage from the main supply rail through a dropping resistor. So, in order to go with other than a separate base bias supply, it is usual to provide the base bias voltage from the main supply rail through a dropping resistor R1. The resistors of R1, R2, R1 and R2 can now be chosen to give a suitable quiescent base current of 45.8 microamperes or 46 microamperes, rounded off to the nearest integer. Here the current flowing through the potential divider circuit has to be large. Here the current flowing through the potential divider circuit has to be large compared to the actual base current IB, so that the voltage divider network is not loaded by the base current flow. And here a general rule of thumb is a value of at least 10 times the IB which is flowing through the resistor R2. Here the base current is very less. General rule will be at least 10 times the IB which the current will flow through R2. The transistor base to emitter voltage, which is fixed at zero point 0.7, because this is the junction voltage which is required for a silicon transistor, and this gives the value R2 is equals to VRE plus VBE by 10 times the IB. That is, here the VRE value is 1 plus 0.7 by 458, 45.8 microamperes is there. So 10 into 45.8, that gives us 458 into 10 to the power of minus 6, which is equals to 3.71 kilo ohms. Now we got the R2 value. If the current flowing through R2 is 10 times the base current, then the current flowing through R1 in the divider network must be 11 times the value of the base current. That is IR2 plus IB. Here, thus the voltage across the resistor R1 is equals to VCC minus 1.7 volts, where VRE plus 0.7, which is equal to 10.3 volts. Therefore, R1 can be calculated as R1 is equals to VCC into VRE plus VBE by 11 into IB. So here, sorry, VCC minus this one. So 12 minus 1.7 by 504 into 10 power minus 6, that gives us the value as 20.45 kilo ohms. And the value of emitter resistance can be easily calculated using the Ohm's law. Here, IE, if we know, we can calculate the RE value. The current flowing through RE is the combination of base current and collector current. That is, IE is equals to IC plus IB, that is equals to 4.58 milliamperes plus 45.8 microamperes, that is equals to 4.63 milliamperes. And here the resistor RE is connected between the transistor's emitter terminal and the ground. And we said previously that there is a voltage drop of 1 volts across it. Thus the value of emitter resistance can be calculated. RE is equals to VRE by IE, which is equals to 1 volt by IE value we have calculated, that is 4.63 milliamperes, where we are going to get this value as 216 ohms. So for our example above, the preferred values of resistors chosen to give a tolerance of 5% are R1 is equals to 20 kilo ohms, R2 is equals to 3.6 kilo ohms, RL is equals to 1.2 kilo ohms, RE is equals to 220 ohms. Then our original common emitter amplifier circuit above can be rewritten by including the values of the components that we have just calculated. And this is the our complete circuit with all the values are included. That is, here the value of the resistance is 20 kilo ohms, 3.6 kilo ohms, 220 ohms, 1.2 kilo ohms, 4.63 milliamperes, 46 microamperes, 4.58 milliamperes. Here we are taking VCE under saturation condition. That value we are considering it as 0. Now we need to go with the coupling capacitors. Here in the common emitter amplifier circuit, the capacitors C1, C2 are the coupling capacitors in order to separate AC signals from the DC biasing voltage. So these coupling capacitors are used to separate the AC signals from the DC biasing voltage. And this ensures that the bias condition setup for the circuit to operate correctly is not affected by any additional amplifier stages, as the capacitors only pass AC signals and blocks any DC component. And the capacitor does not allow the DC component, which will capacitor is going to only allow the AC signals. The output AC signal is then superimposed on the biasing of the following stages. Also, a bypass capacitor C is included in the emitter leg circuit. And this capacitor is effectively an open circuit component for DC biasing conditions, which means that the biasing currents and voltages are not affected by the addition of capacitor, maintaining a good quality good Q point stability. However, this parallel connected bypass capacitor effectively becomes a short circuit to the emitter resistance at high frequency signals due to its reactance. Thus, only RL plus very small internal resistance acts as the load, increasing voltage gain to its maximum. So generally the value of bypass capacitor CE is chosen to provide a reactance of at most 1/10 of the RE at the lowest operating signal frequency. That is nothing but the impedance or reactance offered by the capacitor should be equals to 1 by 10 times the value of the Re. So we can now construct a series of curves that shows the collector current IC against the collector emitter voltage with different VCE values of base current for our simple common emitter amplifier circuit. And these curves known as output characteristic curves and are used to show how the transistor will operate over its dynamic range. Here, a static or DC load line is drawn onto the curves for the load resistor RL of 1.2 kilo ohms to show all the transistors' possible operating points. When the transistor is switched off, VCE is equals the supply voltage VCC, and this is point B on the line. Likewise, when the transistor is fully on and saturated, the collector current is determined by the load resistance RL, and this point A is on the line. And we calculated before from the DC gain of the transistor that the base current is required for the mean position of transistor was 45.8 microamperes, and this is marked as point Q on the load line, which represents the quiescent point or Q point of the amplifier. We could quite easily make life easy for ourselves and round off this value to 50 microamperes exactly without any effect to the operating point. And this is the output characteristics which we are going to get. Here, this is the operating point, that is Q point, that is where IB value, base current value is 46 microamperes and VCE value is 5.8 volts and IC value is at 4.8 milliamperes. So these are the different output characteristics which we are going to have for this common emitter amplifier. Here point Q on the load line gives us the base current or Q point of base current IB is equals to 45.8 microamperes or approximately 46 microamperes. We need to find the maximum and minimum peak swings of the base current, because when we are giving the input as the alternating current, so the base current should have the maximum and minimum peak swings that will result in a proportional change in collector current. When the base current changes, correspondingly the collector current changes. I see without any distortion to the output signal. As the load line cuts through the different base current values on the DC characteristic curves, we can find the peak swings of base current that are equally spaced along the load line. And these values are marked as N and M on the line. Here these values are marked on N and M on the line. These are N and M values on the line, which gives the minimum and maximum base current of 20 microamperes and 80 microamperes respectively. Here these points N and M can be anywhere along the load line that we choose as long as they are equally spaced from Q. This then gives us a theoretical maximum input signal to the base terminal of 60 microamperes peak to peak, 30 microamperes peak. Here we have got the 60 microamperes peak to peak value and the 30 microamperes peak value. That is nothing but from positive to negative, whatever the current which we are having is 60 microamperes. Only the positive and or only the negative peak value is only 30 microamperes without producing any distortion to the output signal. And any input signal giving a base current greater than this value will drive the transistor to go beyond the point N and into its cutoff region or beyond point M and into its saturation region, thereby resulting to the output signal in the form of clipping. Here, using the points N and M as an example, the instantaneous values of collector current and corresponding collector to emitter voltage can be projected from the load line. Corresponding to the base current, we can also project the collector current and collector to emitter voltage. And it can be seen from the collector to emitter voltage, that is exactly 180 degrees away from displacement with the collector current. As the base current IB changes in a positive direction from 50 microamperes to 80 microamperes, the collector to emitter voltage, which is also the output voltage, which decreases from its steady state value of 5.8 volts to 2 volts. Then a single stage common emitter amplifier is also an inverting amplifier, as an increase in base voltage which will causes a decrease in V output and a decrease in base voltage which produces increase in the output voltage. And in other words, the output signal is 180 degrees out of phase with the input signal. Here, the voltage gain of the common emitter amplifier, which is equal to the ratio of change in input voltage to the change in amplifier's output voltage. That is delta VL is del V out and delta VB is the input. But the voltage gain is equals to the ratio of signal resistance in the collector to signal resistance in the emitter. When we are taking voltage is directly proportional to the resistances. So always this voltage gain is equal to the ratio of signal resistance corresponding to the collector and emitter. Here the voltage gain is equals to V output by V input, that is equals to delta VL by delta VB, which is equals to minus RL by RE, minus RL by RE. Here we have mentioned earlier that as the AC signal frequency increases, which will short circuit the emitter capacitance in order to short out the emitter resistance due to its reactance. Then at high frequencies, RE value is equals to 0, making the gain as infinite. However, the bipolar transistor has a small internal resistance built into its emitter region called R-E, where the transistor's semiconductor material offers an internal resistance to the flow of current through it and is generally represented by a small resistor symbol shown inside the main transistor symbol. Here the transistor datasheets provide us a small signal bipolar transistor, this internal resistance is the product of 25 millivolts divided by IE, where the IE value is 4.58 milliamperes. Here 25 millivolts by IE, that is 4.58, which is approximately 5.5 ohms. And this internal emitter leg resistance will be in series with the external emitter resistance. Then the equation for transistors actual gain will be modified to include this internal resistance. So will be voltage gain is equals to minus RL by RE plus RE dash. So this internal resistance will be added while calculating the voltage gain. And at low frequency signals, the total resistance in the emitter leg is equal to RE plus RE dash. At high frequency, the bypass capacitors short out the emitter resistor, which is leaving the internal resistance in the emitter leg, which results in a high gain. When it is short circuited, we are going to get the high current gain, high voltage gain we are going to get. Then for our common emitter amplifier circuit, the gain of the circuit at both low and high signal frequencies, which is given as gain is equals to minus RL by RE plus RE dash, that is equals to minus 1200 by 220 plus 5.5, which is equals to minus 5.32. An amplifier gain at high frequencies only RE dash will be there, emitter resistance will be short out by the capacitor, that is minus RL by RE dash, that is equals to minus 1200 by 5.5, which is equals to minus 21H. Here thus at very low input signal frequencies, the reactance is high. So the external resistance RE has effect on the voltage gain, which is going to lowering, which is going to reduce the voltage gain in this example. However, when the input signal frequency is very high, RE value is 0, where the voltage gain will be increases. And one final point, the voltage gain is dependent only on the values of collector resistance, load resistance, and the emitter resistance, which is not affected by the current gain beta of the transistor. Here the voltage gain is not depending on the beta value. So for our example above, we can now summarize all the values we have calculated from the common amplifier circuit, and these are the base current. Minimum is 20 amperes, 20 microamperes, mean is 50 microamperes, maximum is 80 microamperes. Collector current is 2 milliamperes, 4.8 milliamperes, 7.7 milliamperes. The output voltage swing 2 volts, 5.8 volts, 9.3 volts. And amplifier gain is minus 5.32 and maximum value is minus 21H. Here, with this, I'm concluding this session. In this session, we have discussed how to calculate the values corresponding to small signal amplifier, where the amplifier which we are considered as common emitter amplifier circuit. And we have also taken one example and we have calculated all the parameters corresponding to the amplifier circuit. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.